Hi everyone, welcome back to Prakasham Tutorials. In my previous video, we have discussed about mean squared value of the binomial distributed random variable. Now here in this video, we are going to discuss about variance of a binomial distributed random variable, moment generating function of a binomial distributed random variable, characteristic function of a binomial distributed random variable. So first we are going to discuss about variance of a binomially distributed random variable. So we know that random variable capital X is the binomial random variable. The variance of the random variable X is given by variance of X is equal to expectation of X square minus expectation of X whole square. So this is the standard expression of the variance of the random variable. So this equation is already discussed in my previous videos. In my previous videos, we have already calculated mean value of the binomial random variable and mean square value of the binomial random variables. That are, mean value of the binomial random variable is np and mean square value of the binomial random variable is n square p square plus npq. So these two expressions already derived, already explained in my previous videos. So please refer that videos. Now here we want to calculate variance of the random variable. So what is the expression of the variance of the random variable? Variance of x is equal expectation of x square minus expectation of x whole square. So but expectation of x square, this is the value, and expectation of x is this is the value, and substitute expectation of x square values into this equation. We get variance of x square is n square p square plus npq minus np whole square. Np whole square is n square p square. So plus n square p square minus n square p square is the cancel. We get npq. So this is the this is the expression of variance of a binomially distributed random variable. And next we are going to discuss about moment generating function of a binomially distributed random variable. Random variable capital X is a binomially distributed random variable. Then the moment generating function is given by mx of t is equal expectation of e power tx, which is equal sigma I is equal to 1 to n e power txi into p of xi. And this is the expression of moment generating function of the random variable x for discrete case. So now here the expression is mx of t is equal expectation of e power tx, which is equal x is equal 0 to n. For binomial distribution, the range of x is 0 to n e power tx into p of x. For binomial distribution expression, the probability of x expression is probability of x value is ncx into p power x into q power n minus x. Substitute that value into that expression to this equation. We get mx of t is equal sigma x is equal to 0 to n e power tx into ncx p power x q power n minus x. So using the expansion of binomial, this RHS term is written as p plus q, okay, sorry, and this e power tx into p power x, e power tx into p power x is written as p e power t whole to the power of x. So therefore RHS term is sigma x is equal to 0 to n ncx into p e power t whole to the power of x into q power n minus x. So now applying the binomial expression. So using binomial concept expression, this RHS term is p e power t plus q whole to the power of n. So therefore mx of t is equal p e power t plus q whole to the power of n. So this is the expression of moment generating function of a binomially distributed random variable. And next we are going to discuss about characteristic function of a binomially distributed random variable. So we know that random variable capital X is binomially distributed random variable. Then the characteristic function is given by pi x of omega is equal expectation of e power j omega x, which is equal sigma I is equal to 1 to n e power j omega xi p of xi. So this is the expression of characteristic function of a random variable for discrete case. So now here the expression of characteristic function of the random variable. Now x is varies from 0 to n. The expression is pi x of omega is equal sigma x is equal 0 to n e power j omega x into p of x. But we know that for binomial distribution, p of x is ncx into p power x into q power n minus x, and substitute that expression into here on RHS side. We get pi x of omega is equal sigma x is equal 0 to n e power j omega x into ncx p power x q power n minus x. So now here on RHS side, e power j omega x into p power x is written as e power j omega into p whole to the power of x. So the resultant RHS term is this one. So using binomial expansion, the RHS term is written as p e power j omega plus q whole to the power of n using binomial expansion. So therefore, the characteristic function phi x of omega is equal p e power j omega plus q whole to the power of n. So this is the expansion, or this is the expression of, or this is the derivation of characteristic function of a binomial distributed random variable. The characteristic function of a binomial distributed random variable is also explained, is also derived from the expression of the moment generating function. And what is the expression of the moment generating function of a binomial distributed random variable? Mx of t is equal p e power t plus q whole to the power of n. So from this expression, we can derive characteristic function of a binomial distributed random variable. How to derive, how to calculate? In this expression, t is replaced by j omega, small t is replaced by j omega. We get the expression of the characteristic function of a binomial distributed random variable from the moment generating function of a binomial distributed random variable. So that is finally we get in this case also finally we get same expression. Small t is replaced by j omega. So therefore, pi x of omega is equal p e power j omega plus q whole to the power of n. So this is the concept of, this is the derivation of variance of a binomial distributed random variable, moment generating function of a binomial distributed random variable, and characteristic function of a binomial distributed random variable.